The quarter's coming to an end real soon. Retest. So you're gonna have, I'm sorry, okay, so obviously we're testing on this unit next week, and then the last week of the quarter is for retest. You can only retest if you got an 80 or less. No, I'm sorry, if you got a 79 or less, you can't retest with an 80. And retest will happen after school is preferred. I know you guys like return periods, but I don't know if they're long enough. And we have so many double threes coming up, which means that there's like stuff. I don't know. I just don't feel like I can count on a return. Do you guys feel like you can count on a return to flip? Right? So, and I'll stay after school any day. I also get here at like 6:30 every morning. So if you have sports or something, you can also do the retest early in the morning. I know that just sounds insane, but it is an option. Okay, so let's get started. You should have picked up a copy of the notes, but you're going to annotate just like I annotate. You want to annotate these notes. I'm going to try to go full screen and still annotate. We'll see how that goes. Boom. It's very okay. That's called the walk of shame. This is very strange. Super strange for me. Where's my mouse? Okay. So here I'm trying to show nucleons, and quarks make up the nucleons. So quarks make up protons and neutrons. So if you ever wondered when we say protons and neutrons, what make up a proton and a neutron, it is the quark. And hold on, I just don't know why this isn't. Can I use a pen? Can I use a pen? Will you let me use a pen? Will you let me use a pen? Oh, yep, here's a pen. This is butt munch. This is awful. Okay. So yeah, I can't do this. You guys don't see what I see, but I can't see my cursor. Yeah, I can't do that. That's crazy town. And slideshow. That's crazy town. Oh, stop. Discard. That's crazy town. Okay, sorry about that, guys. Is this big enough for you? Can you see that okay? Should I turn off this front light? Back row? All about you guys, back row. Okay, so here are the quarks. These are the quarks that make up a proton or a neutron. And you see the squiggly lines and squiggly lines and squiggly lines. So they make them up. There are 6 flavors of quarks that we know of right now. And they're called up and down, strange and charm, top and bottom. Isn't that cool? So those are the 6 different types of quarks. Hey, what are we going to call this one? Let's call it up. Let's call this one down. Let's call this one strange. Well, that was kind of mean. So the next one's charm. Okay, let's get back to like not offensive things. So, you know, top and bottom. Isn't that cool? You need 1 quark of each color. Between the quarks are gluons. These guys are the gluons. And they apparently hold the quarks together. Now, how do we know all this? Obviously, this is from the collider so far. The gluon that holds these together. So did you ever wonder if we say we have a whole bunch of protons in the nucleus, why don't they repel? Right? So because like charges repel and it doesn't make sense. So the neutrons in the nucleus, the ones with no charges in the nucleus with these quarks are the latest theory. So it's called the nuclear force, right? We don't understand it. It is 10 to the 9th time stronger than gravity. It's the strongest force we know of, called the nuclear force, that is stabilizing these positive charges. So why don't they repel? We think it has something to do with the neutrons, and we think it has something to do with the quarks and the gluons and the bosons and the Higgs particles. That's what they're researching. We don't know why that repulsion isn't there, but the attraction that forms, that holds this together, is the strongest force that we know of. And it would be really cool to kind of figure that out. But that's probably going to be figured out in your lifetime. Isn't that cool? I mean, you know, if we, never mind. Never mind. That's cool. Okay, so nuclear reactions involve changes in the nucleus. When the nucleus changes, the element changes. So this doesn't happen in chemical reactions. It only happens in nuclear reactions. The product elements are different than the reactant elements, and this is called transmutation. So the reactants are traditionally called the parent. So the parent changes to the products, which are traditionally called the daughter. So you have parent nuclei becoming daughter nuclei. That's transmutation. During that transmutation, to change from one element to another, radiation is produced. We know that as radioactivity. So you guys have heard of radioactivity, yeah? Okay. And then we can measure radioactivity as radioactive decay. So this is kind of a decay is a time-based system on when that transmutation, how long that transmutation takes. So there are 2 types of this transmutation. We can combine elements, which is called nuclear fusion. And this is what the sun does. The sun is combining hydrogen, which has an atomic number of 1 and a mass number of 1. It is fusing that with another hydrogen, which has an atomic number of 1 and a mass number of 1. So those are the parents. And when it fuses, we get, what's our atomic number when hydrogen fuses? What is 1 plus 1? 2. On the periodic table, what element has the atomic number of 2? Helium. So that right there is transmutation. We fuse these 2 together. It takes a tremendous amount of energy to fuse this together. And then you might go, well, look at this mass. The mass number of 2 means that's an isotope. It's kind of a little unstable because helium really should be 4,2 helium, right? This is the stable isotope of helium. So this is an isotope of helium that is being produced, and this is unstable. And if it's unstable, radiation is produced, right? So what is the radiation produced with this helium and the unstable nuclei of the helium? The entire electromagnetic spectrum, right? That's a lot that's coming from our sun, the entire electromagnetic spectrum. Nuclear decay is where a solo atom, a single atom, emits radiation. Oh, so there is fusion and fission. This is what we know of as splitting the atom. So this is what we know of as like the atomic bomb. So we're combining these 2. Splitting an atom would be, let's say you start with uranium-238, and it will notice now my yield sign. So my parent is going to become a daughter, let's say thorium, and radiation. So fusion is when you're putting them together. Fission is when you're breaking it apart. What is thorium? Thorium, I don't remember what thorium is. Anyone have their periodic table out? 90? Okay. And uranium is 92, right? So whatever the radiation is has to be 2, because 90 plus 2 gives me 92. 90 plus 2 gives me 92. So general nuclear reactions require more activation energy than standard reactions. So activation energy is the amount of energy for a chemical reaction to occur. Like striking a match, you need to add that little bit of friction before the reaction will occur. That would be considered activation energy. But nuclear reactions require activation energy. So how do we get that? Require a lot more than chemical reactions are. You may hear that they're always looking for centrifuges to see if it is cyclotrons are just massive centrifuges. And this is a way to add energy to radioactive substances to get the cascade effect to occur. So obviously that's what the International Nuclear Commission is checking out, those cyclotrons. So getting a nuclear reaction requires activation energy, so we have to add it with cyclotrons. But radioactive decay is spontaneous. We don't have to do anything. It just happens. Just happens. And this is general nuclear reactions. We're not getting into the funky ones. So a lot of stuff: fission, atom smashing, fusion, a reaction where they're forced together. This occurs at extremely high temperatures. That makes sense. So, you know, the coveted energy source would be if we could do something called cold fusion. Cold fusion. Really, right now, to get fusion to occur, we need to get it at temperatures that, you know, don't normally occur on Earth. So obviously it occurs in the sun, and during thermonuclear, there are moments during thermonuclear explosions that we reach some fusions. But, you know, we keep trying. Haven't got there yet, but cold fusion would be nice. That's a theory. That's in theory. I don't know if cold fusion can actually happen. It'd be nice, but anyway. So we've talked a lot about the transmutation, and when atoms transmutate, their nuclei release particles, and you need to know the particles that are released. One particle, wait a second. You should have, do you have one more? Oh, wait, no. Oh my goodness. Is this the whole slide? No. There we go. The alpha particle is 4-2 helium or alpha. So an alpha particle, 4 is the mass number, 2 is, what's 2? Number of protons. So if we look, here's a proton, the mass is 4. And an alpha is like that. It's almost like a squatted Jesus fish. You start here. It's like an X where you don't lift up. Or you take a Jesus fish and squish it this way. That's an alpha particle, 4-2 alpha. You may see it referred to as a helium nucleus, but really, now it's called helium nucleus because there are no electrons. So 4-2 alpha is a better description. A beta particle, beta, you're going to do a fancy B. You start low. It's kind of like a cursive B with a long line. A beta particle, get this, has a negative proton. It has, so its atomic number is -1, and it has 0 mass, and that's a beta particle. So we end up having a negative charge. A positron is a type of beta particle. So you still have that cursive B, practice writing that cursive B, but instead it's a +1 with no mass. Okay. Same mass as an electron, but with a 1 unit of positive charge. This is same mass of an electron, but we have 1 unit of negative charge. Nuclei can eject protons. So often a proton can be referred to as just a hydrogen nucleus, like you did in biology. You were always tracing the hydrogens, they were protons, or it's that lowercase p. A proton has a mass of 1 and its atomic number would be 1. And your charge is still positive here. A nucleus can eject a neutron. A neutron does not add to the atomic number, and it's still the little n, that's why we use it for neutron, but it has a mass of 1. There's no charge, and then gamma is this funky Y. So to draw the Y, you kind of make a curve like this first, like a hockey stick, and then bring it together, a little guy. So that is your gamma particle, and there is no proton and 0 mass. So 0, 0 gamma. This is only energy, 100% energy. This picture here is showing that a nucleus can emit any of these. So this unstable nucleus is shooting off an alpha particle, yeah, a beta particle, a positron, and some gamma rays, all in an attempt to become more stable. And it's going to look a lot different after it shoots these guys off. The nucleus is going to be a lot different. It's transmutating into the daughter nuclei. So there's tons of radiation, but the state of Virginia would like you to know 3 types of radiation, and now you know the particles that they come from. So this first top picture shows you the radiation that you need to know. Alpha radiation, remember that's 4-2 alpha. That is a type of radiation. Then we have our beta radiation. Anyone remember what beta was? Does it have, what's its mass number? Mass number's up top. 0, no mass. It's -1. What did I just draw? Positron, right? So -1 is your beta radiation. This is a positron. This is beta. Sorry, that B looks like crap. Well, okay, no, you don't really have to write both of them. And gamma radiation, high energy electromagnetic photon, otherwise known as gamma radiation. No mass, no charge, pure energy. And it turns out it's the most damaging. It's absolutely the most damaging. If we were to rank these, alpha is the weakest. Right? You don't want an alpha ray gun, right? That's not going to hurt anyone. You want a gamma ray gun, right? That's going to kill someone. Beta ray gun doesn't even make sense. So alpha is the weakest, beta is kind of medium strength, and then gamma is the strongest type and most dangerous type of radiation. And I forgot an N in my strongest. Strong, because it's pure energy. There's no mass involved here. Remember Einstein, energy equals mass times acceleration squared, speed m equals E equals mc squared. Right? If we get rid of mass, it's just pure energy. Right? 100% pure energy. So that's the most dangerous one. No, nuclide is just the nucleus, a nuclide, sorry, not nucleide, a nuclide. I don't even know why we use that. We could just say nucleus, but okay. It's just the nucleus of an atom. They undergo decay if they're unstable. And so that's what your card says here. Isotopes can be stable. What makes them stable if the number of protons is just about equal to the number of neutrons? Doesn't have to be exact. That's why it's a squiggly equal sign. Just about equal. Like carbon 6 and 7, carbon 13 is fairly stable, right? Obviously, carbon 12 is very stable, 6 and 6. Carbon 12 is everywhere. It's super stable. It's when either the proton number is much greater than the neutron, or the neutron number is much greater than the protons. As soon as that balance is off, you have an unstable isotope. And when it's unstable, it wants to become stable. So it's going to shoot off radioactive particles, alpha, beta, gamma, or what you need to know, but there's, 6 different types. It's going to shoot off particles to make that nucleus more stable. It doesn't do it all at once. It kind of does it stepwise. And if I'm unstable and I shoot off a particle, it's going to run into something, which can cause him to freak and shoot off a particle, which could then bounce into you and you freak and shoot off a particle, right? So just because there's something called the cascade effect that occurs. And that's what you really want to have happen in a nuclear warhead. You want this cascade effect to occur. And that is why to release tremendous amounts of energy. And I say that it's not what you wrote, but in nuclear power plant, like Lake Anna, we're mostly nuclear power in Northern Virginia. Did you know that? We don't really switch over to coal until more north, but we're mostly nuclear power. In a nuclear power plant, what is that whole structure is to contain that cascade. There are these rods of europium, and it's basically just a physical structure to maintain the cascade in a narrow area. Because the cascade effect. Do you understand what cascade is? One particle running into another that then causes that nucleus to be unstable, which causes the next nucleus to be unstable, and then everyone's shooting out all kinds of radiation. Yeah.
How similar do they have to be? I mean, it could be a balance, and if like 1 or 2 with the number of neutrons.
It varies on the atom. It varies on how it varies on the atom. Yeah.
Doesn't fusion release less radioactivity than?
Yes. Fusion releases less radioactivity so nuclear fusion is great all the way up until iron, Fe26. It's after, basically 26 is so large, it's after iron that, it'll go supernova, and that releases a whole bunch. So yeah, it starts out smaller, but as fusion occurs with heavier elements, more is released. Okay, so that was an excellent question. Oh my God, my chair is squeaking. So you need to be able to represent alpha emission. Everyone, if we're looking here, we're looking at uranium-238. That's an isotope of uranium. This is its atomic number. And I tell you alpha emission. Do you remember the alpha particle? Yes. So it's emitting a 4-2 alpha. Look how easy nuclear chemistry is. So on this side, here's your plus. It's emitting this alpha particle. And to become more stable, This is the parent isotope. Question is, what's the daughter? Well, straight up math. 4 plus what gives me 238? Hopefully you say 234. And 2 plus what gives me 92? Hopefully you say 90. Now you look on your periodic table and you find element number 90. Thorium. Boom. So it's thorium 234 is the daughter isotope after alpha emission of uranium 238. So our mass still conserved, matter's not created or destroyed, right? These two together equal our 238, 90 and 2 equal our 92. So let's do a beta emission or beta minus that it's showing here. It says here it occurs when a nucleus emits a particle, a beta minus particle. It's going to happen with magnesium 27. So what is our beta particle? 0 minus 1 with the B. Whatever our daughter isotope is going to be, I know its mass number is 27 because 27 plus 0 is 27. And then keep your negative sign straight. What is this? What number minus 1 equals 12? 13 minus 1 equals 12. Does that make sense to everyone? So what atom is number 13? Aluminum. So aluminum 27 is the daughter isotope when magnesium 27 undergoes beta emission. Right? This is, again, the parent isotope. This is the daughter isotope. What do you think? Pretty fun? So then let's do positron emission or beta plus with the magnesium. So what's that daughter going to be? Plus 1 beta. So our mass is still going to be 27, but my atom is now 11. So sodium 27, right? The isotope sodium 27. That is the daughter isotope with positron emission. Now notice we're looking at the parent and then the arrow comes right away, right? Parent, arrow, and then what we get. This is decay. This guy's breaking apart into different pieces, right? Electron capture. Electron capture, look at this guy. We have two things on the left-hand side. This is when we bombard something, when we're literally going to smash a particle into an isotope, right? We're smashing a particle into an isotope. So this is kind of downstream from that initial decay. So there are two things on the left. It's no different though. 0 plus 81. I know my daughter is going to have a mass number of 81. -1 plus 37 is what? 36. And then you look on the periodic table and I'm at krypton, Kr. Make sense? That's capture. So remember, we've changed the nuclei, which is called what? When the nuclei changes, starts with a T, transmutation. So practice problems. Radium-213 decay by alpha emission. So this is like what you will have to do on the free response part of your test. And it'll say radium-213 decay by alpha emission. Show the nuclear equation for this. So you find your periodic table and you find radium. It's in group 2. What's its atomic number? 88. Everyone good with 88? Here's your 213. And you see how that can be an unstable isotope, because to be 213, that means it has, you know, if I do 213 minus 88, that tells me how many neutrons, and that's pretty far from 88. It's not an equal amount. When it says it's going to decay, so we do the arrow right away. This guy's going to break down. So we're not capturing it. We're not adding it to, like this guy's not capturing that. It's straight up decay. So the arrow is next. You have to have the particle memorized, the alpha particle memorized. Remember, that's a 4-2 alpha. And then your daughter nucleon. Yes.
It says electron capture, should we just assume it's beta minus?
Well, that's what, yeah, that is the electron. Electron capture is right up here. So krypton is 36. So you're gonna have 0 minus 1 beta plus 36 K R 76. Notice the difference between capture and emission. Emission is like releasing. Releasing. So on the product side. Okay, so I'm going to freeze the screen. You finish these and then we'll see how you do. So let me freeze the screen so you can't see. Ugh. Okay, so this would be 86 and this would be 209 and 86. Okay, I'm going to unfreeze. Don't look if you're not done. Maybe I can. Can I zoom in on that? Oh, geez. Hold on. Yes.
If you're dealing
Oh,
with,
shoot. Yes. Sorry.
you're dealing with like relatively light elements, is the effect that the neutrons have greater? If it's-
Yes. Yes. Another excellent question. You into nuclear chemistry? If it's intuitive, go for it. Go for that. That's what you did. There you go. That sounds pretty intuitive. How'd you guys do? Alpha, beta, gamma, just initial with attitude and you may go.
Okay,
Use your own.
okay. Do I use that stamp or?
No, you just use your own pen and initial with attitude. And that is completely valid. So it's kind of important to memorize the particles, but yes, right. Right. Gamma does not affect, yep. Good point. So let's look at this guy. With the particles, you can figure out which elements will transmutate, change by the equation. Let me get back to smaller. In nuclear equations, the total of the atomic number and the total of the mass number must be equal on both sides. When a particle is on the reactant side, it's considered transmutation. When a particle is on the reactant side, it's considered transmutation. So electron capture is considered transmutation. This is also the transmutation of beryllium with an alpha particle, right? So remember that helium is just an alpha particle. That is just an alpha particle. And the 0 and 1, what is this guy called again? You can look on your notes. But it's just a neutron. Yep, it's just a neutron. Depending on its speed, it's sometimes referred to as a neutrino. Right? So neutrino, depending on its speed. Yes. Mhm. Yep. So here is another very similar to a test question. We have polonium-218. It undergoes alpha decay. This is a decay, not this is a decay. When it undergoes alpha decay, we get lead-214 as its daughter. Let me know if you guys are not understanding this. Again, remember the helium is just an alpha particle. This is decay. Is this decay? No, no, because you got two things on the reactant side. So this is transmutation, which everything kind of is. It's also bombardment. Bombardment. It's also referred to as capture. Anyway, you're pushing these together. Bombardment, that is that whole chain reaction effect, the chain reaction effect. So you got polonium releasing an alpha particle, it's going to run into something. And if it runs into Einsteinium here, boom, that's what this reaction looks like, right? Now you have 99 and 2, and you have 101. You have 253 and 4, and you have 256. So I need a 1 here because this is 257. I need a 1 here and a 0 here. What's this guy? Right? There we go. It's releasing a neutrino. Now, that being said, it could also release this. Right? Couldn't it release a gamma particle? Well, you know, if I tell you that it releases an alpha and gamma particles, you would just write the gamma particle. So the gamma does not really affect it. So the next slide that you're looking at, the next slide that you're looking at. Oh, is represented on this picture. We look at this picture. Right here is what's called half-life. And a half-life is defined as how long it takes for half of a substance to transmutate. So uranium-238 undergo, see that little alpha sign right there? Undergoing alpha decay, well, it takes 4.5 times 10 to the 9 years. That's a lot. And then what does it decay into? Well, the daughter is thorium-234. Thorium-234. Well, that only takes 24.5 days. And thorium decays into protactinium-234, and that will decay in 1.14 minutes. And protactinium will decay into uranium-234 with an alpha particle, and now we're at 2.33 times 10 to the 5 years. Uranium via alpha decay will go back to thorium. Wait a second, it was going to thorium before, but notice the thorium's getting lighter, right? As it's getting lighter, it's getting more stable because the number of neutrons is getting closer to the number of protons, right? So this is kind of like that bombardment chain. So if we're around long enough, lo and behold, we get back to lead. We get back all the way to lead. We got a lead-210 here, but we can go even lighter and we're stable at lead-206. right? We got lead 214, lead 210, lead 206. So we have a set amount. So whatever inherits the planet billions of years from now, a whole bunch of lead around where there was radioactive uranium. And this is the pathway it will take to get there. Does that make sense to you guys? So this cascade can be represented with these equations. So can you find the particle that will be released to give the daughter the thorium? We've done this before, right? This is the 4,2 alpha. 92 and 238. Now skipped, now we're at, so this is thorium 234, so it's going to decay. Thorium 234, it's going to decay, but this needs to be a -1. 91 minus 1 gives me 90. And this needs to be a 0. So this is a beta particle. Right? It's a beta minus, but it's a beta particle. So see how that has the beta decay right there? The beta decay. So we have that protactinium. What's our daughter going to be if we have a 4,2 alpha particle? Well, this will be 230 because 230 plus 4 gives me 234. What will the atomic number be? 89. And then when you look on the periodic table, what is 89? Anyone?
Actinium.
Actinium. Or protactinium. Actinium. Yep, protactinium. So we go a little off here, so we can't follow the thing the whole way. How do we feel about nuclear equations? Huh? How to, what? Huh? You like it? Trust me, it's a lot easier to balance these than it is to balance chemical equations. But okay, so obviously you're going to have to be able to write these and solve these on the test. So learn the particles. Learn the particle. Alpha, beta, gamma, 2 betas, right? And there's this beta, and what's the other beta? Right, this is one of the +1. And the gamma is, right? And I don't want to see a Y. I don't want to see that, right? It's not a Y. It's a gamma particle. So make the attempt to draw a gamma. You don't have to stick with just the 26 letters. You can learn some other letters, right? Because we have alpha and pi and all this other stuff. Yeah, you learn pi in math, right? So take the time to learn how to write these guys. So that leaves us with half-life. Half-life. What are nucleides again? Not nucleotides. These are just nucleuses, right? These are just an atom's nucleus. So just number of nucleuses is n. And it's n times 10 to the third, which just tells you we're at the 1,000th. So we're at the thousands. So 1,000 times 1,000, 1,000 times 1,000. On here, we're at time. This is our initial number of nuclei or initial nucleuses. That's why they said nuclides, because nucleus is hard to say. Initial number. So 1,000. Half-life is described as the time it takes for half of those to decay or transmutate. So they're no longer this nucleus, they're now another nucleus. Well, what is half of 1,000? 500 is half of 1,000. You read over to a decay curve. This is a decay curve. And once you hit the curve, you go down onto the x-axis to find time. Time is on the x-axis. Whatever time this would be, an hour, a second, a nanosecond, 1,000 years, would be called the half-life, right? So T with a subscript minus 1/2 is defined as half-life. Have you guys done half-life in math yet? Okay, so basically, this is how much time it took, according to the graph, to go from 1,000 to 500. And now what's half of 500? Well, 250. Well, how much time did it take to go to 250? 2 half-lives. So if this was 1 minute, 2 minutes would be this data point, right? 2 half-lives. This is 2 half-lives. And then what's half of 250? 125. So that's undergone 3 half-lives. If the half-life of this substance was a minute, how much would be left after 3 minutes? Well, divide it by 2 once, divide it by 2 again, divide it by 2 again, and you would know how much is left. 125 is left after 3 minutes. Understand how to read this graph? Pretty straightforward. I don't know why that keeps popping up. I guess it wants me to talk. There's all kinds of stuff that can go on the y-axis. This is actually a molarity or a concentration. But no matter what it is, look at the amount at the beginning and divide that in 2. So there would be 0.05 here. Read across, read down in seconds, and this is your half-life, right? This is half of starting. This is where you start. Half of the starting, hit your curve, come down, and that is a single, that is your first half-life, T to 1/2. And it says here that's in seconds. So whatever this reactant is, it has a half-life, a single half-life equals 100 seconds. Does that make sense? So looking at a graph, you should be able to tell me half-life as long as you have an x-axis labeled. You should be able to tell me. And this one's already labeled. You can tell me how much is left after 4 half-lives. Well, this is 4 half-lives. Well, this is really hard to read. Thank goodness we have some equations to do. Another one. We're looking at radioactive decay again. What's this? That's how much you start with. And half of 20 is 10. I read over till I hit the dot. So what is my half-life here? 1 week. How many half-lives in a month? 4 half-lives in a month. Does that make sense to you guys? Half-lives in a month. Great. So our goal is to be able to answer questions like this. I don't know why we can't guess. Stop it. Stop it. The length of time. Oh, this is definition. If an element has the half-life of 12 days and there are 50 grams of the element present, how many grams will be present after 12, 36, and 60 days, or 1, 3, and 5 half-lives? So this is about as easy as it gets, right? You probably can do this in your head. How much would be left of the 50 grams after 1 half-life? 50 grams would be left after 1 half-life? 25. So basically you went from 50 to 25, right? And this little arrow, you divided by 2, and that's considered a half-life. That's 1 half-life. So if I go under another half-life, what's 25 divided by 2? 12.5, right? This is our second half-life. All I did was divide by 2 or times it by 0.5. That's our second half-life. And I got 12.5. What is half of 12.5? Yep, 6.25. So how much is left after 3 half-lives? 6.25 grams. What is half of 6.25? 3 point what? 125. 12.5, right? 12.5 times 2 is 25. So that is how many half-lives? Count the arrows. 1, 2, 3, 4. So I'm not at 5 yet. After 5, what is half of 3.125? There's no shame in dividing by 2 on your calculator if you want to, but half of 3 is 1.5, right? 1.5 is going to go up to 1.5625, 1.5625. Right? See that logic? And that works because the numbers are kind of easy. However, we're not always going to have easy numbers. So whip out your card, your formula card before we get started. There's a bunch of different formulas that you can find online, but basically it is all about the final mass, final number of nucleotides, nuclides, final amount of an isotope. It's all about final, which means at the end. It's all about initial, what you're starting with, initial material, however it's measured, final material, however it's measured. So that's what the F stands for. That's what the I stands for. This N, remember, it's just a count, a quantity, whatever. Oh my goodness, that's awful. This is a lowercase n. The lowercase n is where we get interesting. The lowercase n equals the total time divided by the half-life. Total time divided by the half-life. For example, I asked you how many half-lives in a month. So month was the total time. And on that example, the half-life was 1 week. So you got 4. So N is the number of half-lives. Now think of that. Half-lives. Not what is the half-life, how long it takes for half of it to go away, but how many of those have gone by? How many of those have gone by is half-lives, right? How many of those have gone by? That's kind of like where the biggest confusion takes place. So everyone should have picked up half-life calculation practice. Holy crappers, I have taken too long. You will need a calculator. So you've been back there without the notes? Okay. So looking at number one, it's important to identify as you read what these guys are. So here n sub naught is that our initial or our final? That's our initial. And n sub t is at time t, so this is final. You might see it with A's even. You'll see the formula a gazillion different ways. So sodium 24 has a half-life of 15 hours. So T to the 1/2 equals 15 hours. You don't need the unit right now. How much will remain in an 18-gram sample? So we're starting with our N initial is 18 grams. After 60 hours, what is 60 hours? That is our total time, right? The time elapsed, the total time. So we have 60 hours. Now we can find N with this information. So our little n is 60 over 15. And what do we get? 4. So our n is 4. So that's how many half-lives have occurred. That's how many half-lives have occurred. And we want to know the final mass, right? The final mass. So n, oh, let me write it down here. N final is what we're using. N initial, 18 grams. And I'm going to multiply that by my 0.5 raised to 4. Because there's my half-life raised to 4 times 18. That will give me my final amount. Make sense to you guys? Super simple. Now, can you do this? Divide by 2, divide by 2, divide by 2? Sure, until the numbers get wonky. And until we have some real life time, not just 60 hours. Right. So it's good to just learn the straight up way, because these aren't kind of the problems you're going to have on a test and stuff. These are just learning the method. Number 3, polonium-214 has a relatively short half-life of 164 seconds. So that's my T1/2 that I know, and that's 164. How many seconds would it take for 8 grams of this isotope to decay to 0.25 grams? So my N initial is 8 grams. My N final is 0.25 grams. And I'm going to solve, it's asking me how many seconds would it take? So it's asking me for total time. So I can't use this equation. I'm actually going to have to use it with the N broken apart, right? I'm going to use it with the N broken apart, right? Because this is total time and that's half-life. So we'll plug and chug. I'll put my N final. N final is 0.25 grams equals my 8.0 grams, and it's times 0.5. I'm going to just change that half to 0.5, and I'm raising that 0.5 to big T, which I'm trying to solve for, and my half-life is 164 seconds. So now we're in algebra. How do I solve for this? Well, first, let's divide both sides by 8 grams. That way, this goes away. Does that make sense to everyone? And in your calculator, 0.25 divided by 8 is 0.03125, and that equals 0.5 raised to the T over 164. And we got to solve for T. Well, to do that, we're going to use the logarithmic tool. And there are the logarithmic tools are, if you have I don't know, a to the b equals c. No, that's not a good way. Well, I'll just show it to you. I'm not out there. So we're going to take the log of both sides. So if I take the log of this side, it'll be the log in parentheses 0.03125 close parentheses. And if I take the log of this side, it's literally going to pull that exponent to the front. So it's going to be t over 164 log 0.5. I've taken the log of both sides, and basically by taking the log, I'm allowed to pull that exponent into the front, and that's why I take the log of both sides. Now I want to simplify. I want to get t by itself. To do that, I'm going to multiply this side by 164, right? Because that's really 164 over 1. So my 164 cancels. If I do it on this side, I'm going to do it on this side. So 164 times the log of 0.03125. Make sense to everyone? And then to get t all by itself, I'm going to divide this side by the log of 0.5. And that's going to become 1. If I did that on this side, I have to do it on this side. Divide this by the log of 0.5. So in your calculators, I'm going to put 164 times, there's my times, hit the log button, which gives me my parenthesis, 0.03125. You do not have to do close parenthesis. You're going to hit equals. Always you should get a negative number. Then you hit divided by log 0.5. You do not have to close parentheses, so don't. It's an extra keystroke. Enter. 820. It will be a positive number because the log of any number less than 1 is negatives. 2 negatives become a positive. So 820. 820 what? It would take, yes, 820 seconds. Now, why did we have to do all this? Because we were solving for either t or half-life, total time or half-life. If we're just solving for initial or final, we can go with the easier formula. So it depends on what it's asking you for. Turn the page. That is mass. How much would arrive in this mass? Half-life of strontium. How much would remain after 100 years of that? Okay, let's do number 8 because everyone freaks out. Strontium-90 is present in nuclear fallout. Because it is in the same family as calcium, it can be found in milk and later bones. If you start with 1.94 times 10 to the 17 atoms of strontium, well, that's my N initial. That's my N initial, 1.94 times 10 to the 17. How many atoms will remain? So I'm looking for my N final. That's what I want to know. After 140.5 years, so that's my total time, 140.5 years. The half-life of strontium-90 is 28.1, so T to the 1/2 is 28.1 years. So what I'm going to do is I'm going to combine and find N so I can use my simple formula, my super simple formula. Remember, N is just big T over half-life, or the number of half-lives that have gone by. So 140.5 divided by 28.1, and I get 5. So if I look at my formula for my N, kind of the bottom one you copied there, I'm going to use NF equals n initial, because I have my n initial, times 0.5 raised to the 5th. So now I'm just plugging and chugging. 1.94 times 10 to the 17th. Right, and that is times 0.5 to the 5th. So in my calculator, you can go this way or that way. It doesn't matter. Totally doesn't matter. I'm going to go this way just to show you 0.5. Everyone knows to use hat to the 5th. Everyone knows that? Okay, good. Times 1.94. Oh, wait. Sorry, 1.94 second function, and then EE 17. Okay, now, and then I'll do times 0.5 hat to the 5th. Make sense? Equals. And I get this number. I'm only going to use 3 sig figs because I'm given 3 sig figs, 1.94. Yeah. So my answer is 6.06 times 10 to the 15th. And what is that? What are my units on that? Come on, guys, that number is huge. Whatever it is, it's got to be tiny. Atoms, right? Atoms. Is that less than what we started with? Yeah, 2 orders of magnitude less than what we started with. And that makes sense because we went more than 1 half-life. So the number should be less, and that is definitely a smaller number because of 10 to the 15th. Yes.
What button did you say got the E?
Second function. So put in the base number. You're going to put in 1.94. Oh. Put in the base number. Then you're using your second function, the second function, and then you're looking for the EE button, even though it only gives you 1 E. Then you put in the order of magnitude, which was 17. Now, this is also where you would put if it was, you would do minus if it was a small number. You wouldn't use subtraction, you'd use this guy. That's also the last thing you would enter, right? Please use second function EE. Don't use hats and parentheses. Okay, so you are to work on these problems. You are to model exactly what I did. So I want you to identify each variable that you're given. Oh, let's do number 10. How many half-lives need to have occurred if the original sample of lead-212 is 1/2048 its original mass? Right? So we're looking for N, right? Because that's number of half-lives. How many half-lives need to have occurred? That's our question mark. And we're given not even an initial or a final mass, are we? But we're kind of, because it says if the original sample is 1/2048 its original mass. So original mass, what you want to do, or initial mass, is make that 2048 and make your final 1. Does that make sense? So you started with this and you have this. And again, you'll use then, so you'll identify all your variables. So then you will write the formula that you're using. Then you will plug and chug. So what is plugging and chugging? I'll do 1 equals 2048. Right? 0.5 to the n. 0.5 to the n. If I need to solve for n, that tells me this is a log problem, right? So to make this a log problem, a couple ways I can do it. We could pull this over. I guess since I've already set it up like that, sure, let's pull it over, or maybe I should flip it first. Yeah, maybe I should flip it first. Yeah, let's do that. On your card, you should also have this equation, and initial equals n final over 0.5 to the n. I don't know how good you guys are with algebra. Does everyone see that's the same thing, just rearranged? Should I use this one? Sure. Okay. So let's do that. So my initial is 2048 equals 1 over 0.5 to my n. How do I get rid of this guy? Well, if I multiply this by 0.5 to the n, it goes away. If I do it on that side, I have to do it on this side. So I have 0.5, not 2, the n times 2048 equals 1, which is what I had here. So I'm going to simplify by going 2048, 2048. This goes away. Then I'm going to take the log of both sides. So if I take the log of 1 over 201 divided by, oh, clear. 1 divided by 2048 equals the log of 4.88 times 10 to the minus 4. That's that side. When I take the log of 0.5, what happens? N log of 0.5. Yeah. To get n by itself, I'm going to do this and divide by the log of 0.5. Does that make sense to everyone? I got to divide this side by the log of 0.5. I have to divide this side by the log of 0.5. Hopefully you guys didn't have all this stuff. I should plan my space better when I'm teaching. So I just wanted to show you how to put that into the calculator and to not freak out when you have a fraction, just turn it into a decimal by putting it into your calculator. So you would just do log as you did before, 4.88 second function EE minus 4, right? So it's not, it's the -4, and then hit divided by, and that's just the log of 0.5 and up, clear. Oh, because I didn't do it. Okay, so hold on. You're going to take the log of 4.88 second function EE to the minus 4. And then you, oh, no, start. And then you're going to divide by the log of 0.5, close parentheses, hit enter. And I get 11.0008. So what is my N? How many half-lives needs to occur if the original sample of lead is 1/200th of its original mass? 11 half-lives need to have occurred, or N equals 11. All of that to get 11. Aren't these fun? Any feedback at all? What is there a question? We love questions. Yes. Is N the same as what? No, no, no. Beta particle has has no mass. The beta particle has no mass. This has a mass number. That's just a neutron. Neutron. Yep. So that is a neutron. Okay. You just got these notes. You can't be expected to know all this.
Calculator left it, says, I. Calculator, and it looks exactly like that.
Oh my God, look. It's not my calculator.
Yeah.
That's. I would know. I would assume it's yours.
I think it is. I'm gonna.
Because mine are all beat up and usually spray painted, the ones that are in that
Mine's
drawer.
like a weird model, like I've never seen anybody else on this model right here, so.
No, they're older. They're kind of
Yeah.
classic. Take it. Take it. It is not one I recognize. Yes.
This is like the last question we just did.
Uh-huh.
So I don't get, what do you get to the next step from there?
Okay, so you got this, right? If I take the log of this side, I have to take the log of the other side. Right? So I need to take the log of 1 divided by 2048. Well, I don't want to put that fraction in there, so in my calculator, I go 1 divided by 2048 and enter, and that's the number I get. So the log of 4.88 times 10 to the minus.
So why would you not want to set the fraction?
Well, okay,
It's
log
probably
of
less.
1 divided by 2048. And then divided by the log of 0.5 gives you 11. You sure can.
Okay.
You sure can. If you want to, but you took the log of this side, you
So-
gotta take the log of this side.
Okay,
So if you want,
I was just confused when I saw that number.
well, I'm more comfortable with this, but you must be more comfortable with that.
Okay.
And that's so,
Seems like way more research to me and
yeah,
harder to put in.
really. It's comfort level. I guess I'm more comfort. You can kind of understand why I'd be more comfortable with that, right? Yes.
I'm doing it like completely differently, but I'm getting the same answer. Does it matter?
It only matters because I'm grading it. And I asked you to do it this way.
Okay, I can do it. This way.
Yeah.
I just wanted to turn this in. I'm really sorry if this is late.
It's too,
Can't take it anymore.
no,
Okay.
it's a take-home quiz.
Yeah.
What made you think you could do a take-home quiz late?
I'm not sure. I'm
Yeah.
sorry. I finished it on, I think it was Friday. I just wasn't able to get it in at all. Also the checkup for the notebook. I don't think I've done that yet. Should I do that now or?
No,
Next. class?
Yeah,
Okay.
next
you.
class. But I appreciate that.
Yep, thank you. The half-life practice is home.
Yes, yes, finish the half-life questions for homework, yes.
So I have one question about gammas and light.
Uh-huh,
So why is a gamma the strongest?
because it's pure energy, it's more penetrating. We're gonna learn, the wavelengths are smaller, so higher the energy, the faster the wavelengths, so they travel like this, so they can just penetrate deeper. Versus if you look at the alpha particle, it's kind of like a slow radiant wave. It's one what part of the spectrum.
So if it has no mass.
Well, it's pure energy. It's traveling as the wave. It's
So-
that whole wave particle. Yeah, it shoots through your body and destroys your cells, and you don't even know it until later you have the disease, you die, your internal organs are shredded. You know, and you die hours after an exposure to radiation instead of a bullet kills you like that. You see it. Radiation it's just high energy that goes through, and that energy shakes and destroys the molecules in your body.
It causes like a cascade effect in your body.
No, it literally just obliterates the molecules.
Okay, do I need full stamps on my homework? Do
What do you mean full?
I need every single stamp?
Not every single one, no. No,
Thank you, have a good day.
sure, you too.
So we finished all of these.
Yes, please. Okay. Okay.
I've had like several. I have nothing in the car. Basic stuff. I can't wait for this. Samples are baked to perfection.
What are we doing today? Ah, yeah, I remember. I remember now. Okay. Okay. Okay, I need to end my Zoom.